Okay. All right. So this is what we were talking about last time. And I want to reiterate this sink analogy because I blew it last time and I want to make sure I got it really well. Consider that this is one signal line. Not like, oh, it's the bus with 1, 2, 3, 4, 5, 6 signal lines on it. No. Think of this as one signal line with 6 different components connected to it. The component can either be putting on a 1, which would mean add water, or a 0, which means drain the water. Okay? If this component is adding water, and I want this component outputting a 1, I want the sink to fill up with water so the water can flow to wherever it's supposed to go. All right? Now, if this one's outputting water and all the other ones are like, I'm not outputting anything, so let's be a 0. Well, the drain's open. And all that water that got added is just going to drain right out, meaning this whole sink is empty. Meaning that we've put a 0 onto there. But I wanted a 1. And that's because 1s and 0s, when we're thinking strictly binary, yeah, they're the opposite of one another. But we actually have 3 states. On, connected to voltage, connected to ground, neither. Okay? Neither is the absence of both things. Okay? Very important. I know I've said this a lot, but it's key to understand.
Neither there is the
Z.
plug, though the drain is plugged and the sink is off.
Yes, and that means if this one's outputting water and this off plugged, off plugged, off plugged, off plugged, off plugged, the water from here will fill this up and it can flow wherever it needs to go.
And then technically, if the drain is not plugged, it is 0 regardless of the...
That's true. Exactly. If it's an empty line, there's a 0 on that line. There's no water can be on that line. It's sunk. Yeah. All right. Da-da. So we were talking about this awesome design where we had 3, we kind of like picked out where the 3 buses were, the data bus, the address bus, and the control bus. Arguably, it's a bit of a stretch to call this a control bus at this stage, and it's a bit of a stretch to call this an address bus at this stage, but it is, right? This is where the address lines are. It's only going to ever be on the here to here, and same with the control logic here to here, but it's, that's what it is. And then we were talking about how, well, actually, by us controlling the signals on these data lines and the address lines and the control lines, we can make this circuit do stuff. We can actually perform computation. Now, it's a simple computation. It's just moving data around, but we're doing it. All by controlling these bit patterns, by programming this hardware. Simulated hardware, but hardware. That's cool. If it wasn't clear to you, now we're cooking. Now we are okay, it's computer science. If it wasn't obvious before, it certainly should be becoming obvious at this stage. One thing I noticed, I wanted to really re-emphasize here, is what I'm saying in these lines are what I'm putting on these lines, okay? So I set this to 0, I set this to 1, I set this RAM out to 1, meaning data is going to come out of RAM. Register 0, set the address lines. But here, there will be data on this data line. The data on the data line will be from RAM out, from the RAM. I, though, am setting my data inputs to Z. That's why they're gray. So this does not mean, oh, the data on the data line is Z. No, it means the data on these buttons are Z. No data. And so here I've included the clock pulse, but in general, each row corresponds to a clock pulse. Although technically here on this line, RAM out, there is no clock pulse needed, right? Because as soon as RAM out is there, the data's out. You don't need to wait for clock pulse. But if we go down here, where I'm saying, okay, RAM out, register in. Now I'm moving data around from RAM to a register. If I set all of these signals the way I want, clock pulse, it does what I want. This will then take the data from here and actually put it into here. What's the next line doing? RAM in, register out at a different memory address. So we're now moving data from RAM to the register back into RAM, but in a different memory location. Cool. We are programming and performing computation by controlling these signals. We are manually controlling the signals. But like I was saying last time, wouldn't it be great if we could get the system to kind of control its own signals? Which is something we are obviously going to be working towards. All right. Did we have any questions about what we were doing last time? If you're not that comfortable with this, I strongly recommend going to digital, opening the circuit, and playing around. Someone give me a bit pattern.
0, 1, 1, 0.
Where do you want me to put it?
Register 3.
There's only one register. You mean RAM address 3?
Yeah.
Okay, 1, that's that one. Whoop. RAM in, clock pulse. Boom. Okay, cool. Let's confirm that it's there by saying RAM out. 0, 1, 1, 0, it's there. Whoop. Whoa. Right? Cool. Now, for fun, let's put that into the register. Great. Now, let's put that into RAM address. Nope. RAM in, register out. So we're going to put that into RAM address 2. Whoop. 1 and 0. So now all the contents of RAM should be 0, 1, 1, 0, right? Well, let's find out. RAM out, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0. Cool. Cool. So what did we do? We set the signals 0, 1, 1, 0, put into RAM address 3, 0, 1, 1, 0, saved it. Then we took that value, put it into the register, and then we took the value from the register and put it into RAM address 2, 1, and 0 as well. That's what we did, just by controlling those signals. That's it. Highs and low voltages. Pretty cool. It's very important to have a pretty good understanding about what we just did before moving on in the course, because the rest of this is going to be based on this. Yeah?
When we get to the point when we are making the computer control itself, like instead of your manual inputs, would those be synchronized with the clock, or would they be separate?
So, it depends. Within our system, everything will be synchronized with the clock, and it will work. But if we were to physically implement it, we might run into a bit of a problem. So, who in here has ever been to my office? Are you for real? All right, well, behind me in my office, I've got a giant breadboard with a computer on it, right? And on that configuration, I'd have it synchronized with the clock on the down pulse. So the controls get set when the clock goes down, and then the execution happens on up. So it's kind of like,
But it's still synchronized.
it's synchronized with the clock, but it's happening a half step in between. But for ours, we could do everything on the clock pulse. It'll be fine.
Yeah. I'm just saying though,
It's still
those
synchronized.
things would
Yeah.
be synchronized with it,
Yeah.
because that's how the computer gets controlled.
Yep. Yeah, exactly. Yeah. Pretty cool. All right. Come on. All right. Last chance for questions about what we just did there. Okay. Of course, it's not last chance. All right. Half and full adder. Now, I actually made you do this on like lab 2 or something, without telling you. But anyways. We've got bits, right? Zeros and ones. And we can think of these zeros and ones as numbers, right? Binary numbers. And we saw that we can add binary numbers together, right? Right? That was easy. It works the exact same way as decimal, except we only have two symbols. So if I have like 1, 0, 1, 0 and add 1, 1, 0, 1, what do I do? Okay, 0 plus 1 is 1. 1 plus 1 is 2. 0, carry the 1. 1 plus 0 is 1. And then 1 plus 1 is 2. Right? And then, oh, okay, there we go. Like it works like that. Right? Now, take a moment. Well, I don't want to get ahead of myself. So, memory was created using flip-flops, which are a form of sequential logic. Okay? Whatever the lab we just did was called like the sequential logic one. Okay? Sequential because like what happens, there's like a temporal aspect. Things happen in sequence. Then there was combinational logic. That was like the decoders, multiplexers, demultiplexers, and programmable logic arrays, where it wasn't like stateful. It was just inputs, outputs, right? There was no like temporal aspect to it. Now, don't get me wrong, we're going to take combinational logic and add it to sequential circuits to make use of them in bigger sequential circuits. But in and of themselves, they're not sequential. But the flip-flops are sequential. We use combinational logic to perform those other logical operations. Now, combinational logic is going to be used to perform addition, arithmetic. Now, I can't remember what you call this, but we can derive like all of our basic arithmetic with one operation, increment. If you can increment something, we're actually going to skip increment here. We're going to do addition. But if you can increment something, you can perform addition. Because if you say like x plus 5, that means, when I say increment, I mean add 1. Okay? Count. If I say plus 5, you increment 5 times. That means perform an incrementation 5 times. Right? If I say subtract, that means, okay, increment the other way. Fine. If I say multiplication, that's like a second order operation where it means like, okay, increment 5 times. Right? And division is the inverse. And then we can say the same thing about like to the power and logs, which is like increment 5 times, 5 times, 5 times. But again, these are all based on if we can count, we can do all these things. So we actually don't need a lot to be able to perform arithmetic. And we're just going to do addition. So we're skipping increment. If you can do addition, you can increment. But anyways. So yeah, we're going to use combinational logic to perform addition. But it's going to be very clear very soon that our addition is actually a rather unsophisticated logical operation that I made you do in a lab already. You just didn't realize it. So, if one wants to add 2 bits together, how many output bits are needed? Well, potentially 2, right? Because input 1, output 0. Sorry. That's a 0, but I mean like, okay, 1 input, 1 input. Let me work on my words here. An input, 0. Another input, 0. That gives me a 0. An input, 0. Another input, 1. That gives me a 1. A 1 and a 0, a 1. But then a 1 and a 1, we get a 1, 0. Okay? All right. So we can see when adding 2 1s together, we need like an extra thing going on here. We need a carry bit. We need to be able to carry. In the same way that we do that with decimal, right? If you go 5 plus 5, well, we need a carry, right? We need another digit. By the way, you'll only ever need one more digit. You can't have a position where, like, oh, can I have 2 one-digit numbers and get a 3-digit number in the end with addition? No, you can't because, like, you can't, right? 9.99999 9.99, right? We're going to just get closer and closer and closer to, yeah, right? But we can never really get there. Anyways, so in the same way, it would work in binary. We would never need another bit. All right, so when adding two bits together, two output bits are required because one of those cases requires that carry bit. In general, when adding two n-bit numbers together, n plus 1 bits is sufficient to output the correct sum, like I was just showing you here. Like you just can't, let's see if we can explain that. Remember, adding a bit doubles the number of representable values. Okay, consider this, right? And this would work with decimal too. If you add another digit, you multiply it by 10 in the number of representable values, right? Right? Like in binary, if I have 1 bit, I can represent 2 values. If I have 2 bits, I double the number of values I can represent. In decimal, if I have 1, if I have 2, I now multiply it by the base. I have 10 times the number of values I can represent. But we're dealing with binary, right? So if I have, adding 1 more bit doubles the total number of things I could represent. If I have the largest possible, okay, so n plus 1 bits would give me double the amount I have that I can represent of n, right? Yeah? If I have the biggest n value possible, and I add it to itself, the other biggest n value possible, the biggest possible number I could represent is something twice as big of itself, right? So we would only ever need 1 more bit. Okay? If you don't believe me, just think harder about it. Anyways, not overly important. Okay. So consider the below table showing the result of adding two 1-bit numbers together. A and B are the two 1-bit numbers. S is the sum bit, and C is the carry bit. We were talking about addition, but I feel like if I show you 2-bit addition like this, it becomes pretty friggin' clear that it's just a function. It's just a logical function, right? If this is the input pattern, I output that. If this is the input pattern, I output that, and so on and so on. In fact, I think it was in one of these labs. Let's see, one of these labs. This one? No, not that one. Maybe it was on the assignment?
What were we talking about? When we add stuff together?
No, I somewhere, maybe I took it off. I could be wrong.
You know what it is.
Well, just give me a second. I gave you that table on an assignment or a lab or something. I gave you this table. I think I even gave it like C and S, like carry and sum, and made you implement it. So you've already implemented this. By the way, I just tricked you into doing it because when you put it as just a logical function, it's obvious. It's just a logical function. Okay, I build the circuit to do this. Okay, we can do that. Obviously, we want to have like elegant designs. It always feels good to flex your brain muscle to have a nice design. But when in doubt, what could we always resort to create this type of logical function? We have a special name for this. Programmable logic arrays. Remember, programmable logic arrays are those like brute forceable designs. Create every possible combination of inputs and you AND them together. And whichever series of inputs you want, for whatever output, you OR together to get to the output. We'll see an example of that shortly. But anyways, we did this already. It's funny to think like, okay, yeah, it's addition. And then go, oh yeah, I guess addition really is just this logical operation. It's just like logical function. Okay. Referring to the table above, notice how it's effectively a logical operation. When both inputs are 0, output 0, 0. When 1 is 1, output 0, 1. And when both are 1, output 1, 0. Easy peasy, right? Yeah? Looks pretty much exactly like that, right? Look, what is this column? What's that column? Yeah. Now you jumped the gun. But let's say we wanted to okay, I need to make this, how do we do it? Well, we could use a programmable logic array. Simple, right? This is a programmable logic array. An array of AND gates and an array of OR gates. There's only one, because only one different pair of combinations do I care about S. I don't need an OR gate when there's only one thing going to the output, right? Remember, the point of the OR gate was to make it so that you wouldn't have two outputs high on a single line at a time. If I only ever have one line going out, I don't have to worry about that, so there's no OR gate there. I could draw, maybe, can digital even allow, I'm curious, will digital let me to make a one input bits? One? Nah, it won't, all right. I wondered if it would let you and it would just do nothing really, but.
You could just connect the same line to both.
That's what it would be. Yeah, I guess I could have done that, yeah. But that would have been rather silly. Anyways, look, every possible combination, off, off, on, on. This would be input 0, 0. What do I get? Nothing is out. Nothing is high, right? 0. So this line here goes nowhere, and that's entirely fine. I only include, you might say, what was the point of including that? For visual clarity, I think. When I see a 0, 1, go to S, or a, 1, 0, and then a 0, 1, go to S. And when they're both on, turn the carry bit on. Right? There. We can brute force this with a programmable logic array. When in doubt, programmable logic array. Learn to love them. They're fantastic. However, as already pointed out, if you pay special attention to, wait, that's just AND. And that's just exclusive OR. If you pay special attention to that, you'll notice we could just do exactly that. Take the inputs, exclusive OR them together, that's your sum. And if they're both high, and you get your carry bit. Easy peasy. So what did I say here? Programmable logic arrays are sufficient. However, it's kind of like a brute force solution. Nothing wrong with it, but at this stage, you're always kind of left going like, can we do better? Brute force, it's kind of, ham-fisting a solution, right? It is possible to greatly simplify the circuit and use less gates transistors, which is always a good optimization. It's funny, because when we're writing code, we think about optimization. If you're an engineer who's building something like this physically, yeah, you might want to reduce the number of transistors your design needs. And transistors, like the gates, right? So this is something that, we should be aware of. This is going to be an engineering consideration. Referring to the above table, notice that the S is only 1 when either the inputs are 1. That's just XOR. C is 1 only when both inputs are 1. That's just AND. A few basic gates. XOR is a fancy gate, fine, but it's still a relatively simple operation we're all pretty familiar with. So in other words, instead of using 5 gates for the programmable logic array, which again I know we can be like, well, we don't really need this gate. Fine, we can reduce the number of gates, but still. Instead of needing a programmable logic array, we could reduce it to needing only 2 gates. And below is a special configuration, is a typical configuration that you would see of what we call a half adder. Right? And for the fun of it, let's see it in action. Is that a question, or are you just scratching? Cool. Up, arithmetic, half adder. Cool, cool, cool. Right? So 1, 1. Right? Cool. And I've got the tests there if you really want to edit, right? It's just that truth table. Okay, cool. Oh, cool. Any questions about this half adder thing? Now, it's called a half adder for a reason, because this can only ever add 2 bits together, right? Adding 2 1-bit numbers together, okay, great. What if I have 2 2-bit numbers I want to add together? Well, we've kind of got a problem, right? Like, because like the carry, right? I need the carry needs to, like, here's what I mean. If I go here, let's say, okay, let's take this design, right? If I do that, right? And you're like, well, let's do 2, right? Let's if we want to add 2 2-bit numbers together, well, this carry needs to like be able to be fed back in somehow to the sum of the next bit, right? Like 1001, 1001. Right? If I do 1, 1, okay, 0, there's the carry, but I need to include the carry, like this carry here, assuming this is the least significant bit, this one, and we do the addition, I've got a carry. I need to include this carry bit in the addition of these ones.
You would use associativity for that?
What do you mean?
Like the associativity law of like adding?
Maybe.
You have to add 3 things together. Right?
We do have to add 3 things together. Okay, I see what you mean. Yeah, you'll see in a second how we do it. So yeah, we got a bit of a problem. It's a half adder because it can't really do the full addition. It's, we're getting there. But this is the idea of a half adder. Unfortunately, a half adder is only capable of adding 2 1-bit numbers together. To add with more bits, one may be tempted to chain half adders together, but like we were just saying, we have no way to address that carry bit. Think about regular base 10 addition. If the sum of one digit is greater than 10, really is greater than or equal to 10, the value is carried over and included in the sum of the next digit, right? 77 plus 24, right? Well, that's a 1. But we have to carry this and do 7 plus 2 plus 1, right? We got it. So there's the problem. And this is a problem. This should be, if the sum of one digit is greater than or equal to 10, right, we have to carry over. So thus, the half adder must be modified in some way to incorporate an input of a carry bit into like the next significant bit as we go. So this is where a full adder comes in. A full adder is a circuit designed to add binary numbers of arbitrary size. Now, the full adder itself, like when you think of like the like logical unit of a full adder, it will only ever add 2 bits together, but we can chain them together. That scales such that we can add arbitrary sized binary numbers together. But each like unit will only ever add 2 1-bit numbers together, but we can scale it. So the idea is the same as a half adder. They provide a way, but they provide a way to input a carry bit into the to be accounted for in the next bit's sum, the next significant bit sum. Below is that table. So before we start thinking about what the design is, let's think about what would this table look like. Okay? So here I have A and B, and let's ignore the. I guess we're not going to ignore the carry bit. Let's just think about this in terms of the logical operation, okay? Not the arithmetic, the logical operation. Yes, it's exactly the same thing, but I think it might help. So, if we see a 0, 0, 0, well, carry and sum is 0. 0, 0, 1, so we see a carry bit, well, that's 0 and 1, right? 0, 1, 0, 0, 1, 0, 1, 1, well, we got to set the carry bit high. 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, 0. So far, pretty normal, right? Well, whenever we have 2 bits high, we increase the carry bit. But the special thing here is when we see 1, 1, 1. When we have 3 ones, what do? Well, 1 plus 1 plus 1. Think about it. 1, 1, and we have a carry bit coming in. Okay? Well, that's 3. Okay. That's 3. Right? Right? It would work the same way with decimal. Right? 7 plus 2 plus 1, that's 10. Right? It's just what it is. And you know. Now, mind you, here, it's entirely possible that, well, that carry bit may have been thrown to some other bit that may or may not be here, right? If there's no bit there, it's a 0, right? And then we would just add it down to here. I'm seeing scrunched faces.
Should it not be for 1, 1, 0? Should that not be a 1 in S and a 0 in carry? Should it then be 1?
This 1, 1, 0? Well, what is 1 plus 1 plus 0? 2. So 0, 1. Like the carry bit's high. Right?
It's the same as 0, 1, 1.
All it really matters is whenever there's 2 bits that are high, 1, 2, 3, 1, 1, yeah. It's carry high, sum 0, right?
If you have an odd number of ones, then it's S.
Other questions, thoughts, concerns, comments, anything? Have a look at this. Don't think about the design right now of the circuit. Just think about, does that make sense? That is the definition of the logical operation. Okay, if that's true, does that correspond to the actual arithmetic? And I'm pretty sure it does. So again, observe each input independently and find the pattern. So input each output independently, right? So what's the pattern here? Well, like you said, sum seems to be when there is an odd number of inputs, like high inputs, we output a 1. When it's an even number of inputs, we output a 0. And if you remember, actually, that's what like a multi-input exclusive OR does. So that's kind of nice to know. Now, we're not going to use a multi-input exclusive OR. We're still going to use exclusive ORs, though. But when you chain exclusive ORs together, it does that like parity check, the like even odd thing. And then carry is if B is high and C is high, or if A is high and C is high, or if A is high and B is high, it looks like. Or A is high and B is high and C is high, I guess, too. There's a lot of, right? That's when the carry out is high. So there's some ands and ors going on. Let's think about this, right? So S is only high when 3 of the inputs are, when 1 or 3 of the inputs are 1, when an odd number of inputs are high. Again, this is exclusive OR. And C is 1 when any combination of 2 or more input bits are 1. So A and B are both 1, A and C are 1, B and C is 1, or A, B, and C are 1. Okay?
You have ands for each of those 3 and then OR them together.
Yeah, and, but there's like ORs between each of these things. So, okay, and, OR. And we just have to connect the dots then. Now that might feel like a lot, but if you really slow down and take the time and say, what does that, like, what does it mean? Like, what needs to be true for this to be the case? And look for that generalization, like we just did right here. There's no magic to it other than that. If you find out what it means, like logically, then you just build it. Now, C out can be simplified to check if A and B are both 1, or if the sum of A and B is 1 and C in is 1. So we're actually going to simplify this circuit even more. So we could have hacked it together with a programmable logic array, which, did I do that? Discard. Half adder with PLA. Okay, I did not. So we could do and OR them together, but we can actually simplify it to if A and B are both 1, or if the sum of A and B is 1 and C is 1, which would also, yes, which is still doing the same thing. It's just a little simpler, right? Again, optimizing the number of gates. So here we go. All right. We're chaining those XORs together for the S. When you do this, it's that even odd parity check. And then what are we doing? We're checking if A and B are both 1. That's the A, that one. Or if the sum of A and B is 1 and C is 1. So the sum of A and B is this one, and C in is 1. We AND them, and we're just checking, well, either of these cases, then we see out. This is our full adder. Learn to love them. And this right here is like, look, we created RAM with sequential logic circuits. But at the end of the day, I'm not saying they were easy, but the designs are simple. We can store data. Now we can perform arithmetic. And I mean, being able to just do some number crunching, that's what your computers do. So we now have a way to like do some number crunching and store data. That's unbelievable, right? So this is a full adder. And for the sake of demonstration, let's discard. Full, yeah. Nope, don't look at this yet. No. There, full adder, right? Just let's make sure it makes sense. 1, 1, 1. Yeah. Yeah. And then finally, okay, I shouldn't, yeah, all of the input. There we go. Cool. Right? Was that a question back there? No? Okay, cool. So, okay, I was talking about chaining them together. Well, this still only adds two 1-bit numbers together. Kind of, because we have that carry in. But if I want to start doing more, all I really have to do is like take this, paste, no, come on. Okay, and then instead of having the carry out here, because I don't really give it, like I don't care about that, really what I want to do is like, there. Wait. There. And then, okay, let's make this a little nicer. There. Now, let's see if that'll do the trick, right? So let's add 1, 0, and 1, 1 together. So let's add 2 and 3 together. So let's pretend we've got, okay, 1, 0, and 1, 1. So this will be input A, input B. And this is the least significant bit, most significant bit. What should the answer be? 0, 0, 1, right? Is that right? No. Why did I, there. 0 plus 1 is 0, everybody. There, that's better. 4 plus 1, 5, right? 2 and 3 make sense. That might be too high. Could you see that? Yeah. All right, so let's see. So I'm saying A is 1, 0, so 1, 0, and B is 1, 1. 1, 1. There's no carry in for the least significant bit. Then we go, okay, 1, 0, 1. 1, 0, 1, right? This 1, this is the carry out. This is this S is the middle one. Obviously, it's the 0. And then the top one is the least significant. And if you want to keep chaining these, you just keep going. And my goodness, we are way past time. Anyways, hopefully you had some fun.